In this video, we're going to introduce a new integration technique called integration by parts. Just to remind you of the context so far, we've looked at integration or anti-differentiation for simple functions, things like the integral of x squared is computable by adding 1 to the power, dividing by the new power, and adding our plus c. We've also looked at substitution integrals when we've had something that was more complicated, something we couldn't simply anti-differentiate by inspection. However, those are not sufficient to cover all the possible integrals we would be interested in. For example, if we tried to integrate x times e to the 4x, if we tried a substitution, one of the options might be choosing w to be x. That pretty quickly leads to absolutely nothing happening at all, because all we would do is rename everything in the integral as a w instead of an x, which is not that helpful. So we would ignore doing that. The other option might be e to the 4x, but we would not be able to cancel that x out front. We wouldn't have that classic substitution pattern of an inside function and the derivative outside. So neither here leads to a simpler integral. And so we need a new technique. This particular integral can be evaluated using something called integration by parts, which we'll introduce here. The closest relative to integration by parts on the differentiation side is the product rule. Imagine we had two functions, u and v, and we differentiated them. Well, we would get du dx times v, derivative of the first times the second, plus the first u times the derivative of the second. Now, what would happen if we integrated both sides of this? Now, this seems a little odd to do, but bear with us here for a moment. Integrate all the terms. That should also be equal. This first term, if we have uv, then we differentiate, then we integrate, that should get us back to where we started. A little glossing over constants, but the idea is we take a derivative and then an antiderivative, we get the original function back. The other ingredients here aren't so obvious. In fact, there's not a whole lot we can do with these. So we'll just leave them as is for a moment. How does this get us any further ahead? Well, what we can do is isolate one of these terms. Let's take that one there and write it out by itself. If we do that, then we would have uv on the other side, and we could move this other integral over to the right-hand side. And again, not too obvious where this is going, but this would be an equality based on the derivative rule for products and then integrating that result. This is a true statement. The question is, how would we find it useful? Well, the surprising element is that this is letting us transition from one integral, so a first integral here, that would be something we're starting with, and then we can trade for a second integral. And as with substitutions, where we also developed a new integral from a starting one, hopefully a simpler one. So very much a theme in our integration techniques is having one integral to start with, manipulating it somehow to get a new integral. This doesn't solve the integration problem, but it hopefully gives us something that we can integrate by inspection. Now, this notation that we've used here is factually correct. When it comes to actually evaluating these integrals, there's some short forms that have developed over the years. And if you take a quick look at this, u dv, du, and v here on this next page is how it is summarized more typically. The integral of u times dv is equal to uv minus v du. You will be asked to memorize this formula. It is fundamental to the approach we're using here, but with practice it becomes essentially automatic. We will look at some examples momentarily, but for now let's walk through the process. The idea is this is our given integral. what we're going to do is choose part of the integral to be called u, and everything else, the remaining part. So everything in this whole integral will be either in a u term or what we're going to call dv. If we see where we're going next, I have a u in what I've started with, but I have a du in what I'm trying to create. So how do we connect those? Well, we differentiate the u to get the du part. I also have a dv to start with, but I want a v. Well, we're going to integrate the dv part to get a v. Once we have those building blocks, we'll be able to fill in this right-hand side of the equation, and then we check, hoping that our new integral is actually easier to evaluate than what we started with. So we're hoping that this new form is nicer than the original. We'll work through a number of examples of this, and that'll help you ground this very generic theory with some practical applications.